Okay, we are starting now. Okay, so now we are recording. Okay, so the idea, remember when we were doing the synchronous generator, we would have the generator, the machine, the synchronous machine set up here, and we would provide a mechanical power into it. And out of that, we would get 3 phases of line 1, line 2, line 3 of the electrical power. All right. So this will be mechanical power. And we were converting that thing into electricity. Electrical power. All right. Pretty much, so this is as simple as this one gets. Okay. Now we're going to do something else. So we're going to, instead of going this way, we are going to turn the stuff around and go that way. So we're just going to turn the electrical power into mechanical power. Everybody's still on board? Maybe I should put that on test. Okay, so what was happening in the generator? We would have the 3 stator windings, the 3 phase windings. Phase 1, phase 2, and phase 3. And you were able to measure the voltage across each phase, and you were able to measure the current going through each phase, and you were able to tell how much of the excitation power you have to supply for the rotor. Okay, to excite the field. Okay, what do we need to excite the field? To produce an electromagnet. So here is the idea of the synchronous motor. All right. Well, I'm just going to draw the windings. These are windings, and they are going to be connected in the, just like that. They're going to be connected in the Y connection, with the same as we connected that in our lab. Okay. Now we're going to provide power to it, 3 phases. All right. Phase 1, phase 2, and phase 3. Okay, or line 1, line 2, line 3, whichever you want to do. And they are pretty much 120 degrees, not 180, 120 degrees out of phase. Okay, so here's a sine wave that is inserted into or injected into the phase 1. Phase 2 is going to be the same thing, and phase 3 is going to be the same thing, except that is shifted 120 degrees, that is shifted 120 degrees, and 120 degrees more. All right, so 120, 120, 120. Okay, in this case, we are going, what's going to happen is when we have those 3 phases like that, and I'm just going to draw it a little bit different now. Okay. Oh, can you hear me okay? Am I speaking too loud? Am I speaking too quiet? Not all the classes are recorded. No, not all the classes. Yeah, okay, I guess we just covered that. All right, so let's say we have a winding here. We have a winding here. We have a winding here. Okay, these are windings. There, that way, and that way. And this is the stator. So this doesn't move. I'm just going to lower the light a little bit so you can see the writing on the board a little bit better. Okay, you see less of me and more of the writing on the board. Okay, not too dark. So now, when we supply those the power the waveforms, the phase voltages or the phase current into those three phases, and they are 120 degrees apart from each other, right? The waveforms. So the field is going to build and collapse here, build and collapse here, build and collapse here. It's also going to build and collapse here, build and collapse here, and also is going to do the same thing. But when you go the three phases, it's going to build, 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 like this, like this, like this, like this. You know, okay. I'll have to use three like that, like this. Okay. I hope you get the picture here. All right. What's going to happen when the magnetic field builds, and it's going to build sequentially. So even though the stator is not moving here, but the magnetic field rotates around it. Right. So the magnetic field that this is going to produce is going to create a field that rotates. Right. What is going to happen is that if we have a permanent magnet here, north and south, and if that is basically on an axle, so we can spin it, all right. That permanent magnet is going to follow that field and is going to start turning. Right? However, we usually don't use the permanent magnet situation here, but what we do is use something that's called electromagnet. So we got something like that. There's a winding here, and remember we are supplying a DC power here, and over here is phase 1 AC, phase 2 AC, and phase 3 AC, and they are 120 degrees out of phase. Okay. So now when we have that, okay, so somebody else says, how is that going to happen? Because there are wires connected there are wires connected to this. So once we kind of start turning that, we're going to just rip the wires off, right? Well, there are something that's called slip rings, okay? Almost the same idea as the commutator, but it's a little bit different. There's one ring that is inside, and the other ring is on the other part of the axle, and there are brushes that are touching it, so there's no hardwired connection as far as being able to break the wires, right? So now when we supply the DC power into that, we're magnetizing this north and south, right? And then we have a control over how much to magnetize it and how much not. All right, so we have control over how strong of a magnet we're going to make out of this one. So what's going to happen? We have a revolving or rotating or revolving magnetic field, and we have a magnet that's pretty much electromagnet that we magnetized a metal bar here. All right. So now this has a polarity, magnetic polarity, north and south, and that is going to start following that rotating magnetic field in the same speed that it rotates. Okay, so that's why this motor is called synchronous motor again, because this electromagnet is going to synchronize with the revolving magnetic field. So here's the stator, it doesn't move. This rotor, of course, moves. So we are supplying electrical power to the stator windings. We're supplying electrical power into the field, right? And then in return, we're going to make this thing turn, this rotor. So we're turning the electrical power into a mechanical power. And that's all there is to it as far as being simple. Okay? Now, we're going to talk about a little bit more about how much. Okay, remember when we were doing the saturation curve, no load saturation curve? What happens, and we're going to also do some calculations that have to do with that next time we see each other. Basically, what happens when you apply a little bit of DC power into this metal bar and the coil that is wound around this metal bar, then we're going to magnetize it a little bit. All right, we're going to crank it up bit more. So if we get more DC power applied to that, we're going to magnetize it more. And we increase it, we're going to magnetize it more until it reaches the saturation point. Okay. So when this electromagnet reaches a saturation point, that means no matter how much more we're going to power we're going to provide, it is going to only magnetize so much, and it's going to magnetize no more at that after that point. So that's the saturation point. Okay? And also, what's going to happen? We can under-excite, or we can over-excite the field, or we can excite it just right. Okay? So we're going to talk about that as well. Okay? So let me just all right, so then what else we're going to do during this lab that we're going to, and I encourage you to make notes as well as we talk, because we're gonna, I gotta give you some tests sometime soon, too. And of course, the test is going to be on everything that we talk about, all the calculations that we did, and we're going to do later on, and all the knowledge that we get during the labs. All right. Okay. Okay. Can we get exercise like the next Oh yeah. That's what I said. Next time we're going to see each other, we're going to do some calculations and exercise. I just don't want to mix one and the other, the concept and the exercise together. It's just my style. All right. What was I going to show you? Okay. So in our lab, we're going to have the synchronous motor. Right. Synchronous machine. We're going to use it as a motor. All right. Then we're going to connect that thing into the torque meter. And from the torque meter, we're going to connect that into a DC. And we're going to use that DC as a generator. And that DC generator is going to be connected to our load, like this here. And they're going to be resistors, and so on. They're going to continue, and and these are the switches. Right. So that's how things are going to be connected. So basically, this DC machine, we're going to use it as a generator, and we're going to keep loading it to a certain degree in order to make this thing work harder, or not so hard, depending on the exercise that we're going to perform. Right? Now, remember some of you guys I asked to take a picture of the load bank. I encourage you, whoever hasn't taken a picture of the load bank, take a picture of it next time you're at the lab room. And basically, those three banks that we're going to connect, there's going to be bank number 2 and bank number 3 here with resistors and switches. We're going to connect that to that, and that to that, and this to this, and that to that. So that means this is the most stupid phone ring I ever heard, but it's okay. So those three load banks are going to work. So we're going to make one big parallel array of resistors. Okay, and based on that, we're going to close on the resistors. So it means every time we close a switch, we're adding a resistor, but because they're in parallel, that means we're not adding the resistance. We're going to decrease the resistance. Okay, so when we get this here, this resistor and that resistor, We got, let's say, 100 ohms here and 100 ohms here, or let's say, okay, that one is 400 ohms and 400 ohms here. So when we close this, we're going to get 400 ohms. When we close that one, we're going to get not 800 ohms, but we're going to get 200 ohms, because two resistors. And then every time you're going to close another resistor, you're going to provide yet another pathway for the current to go through, which means it's going to be easier to flow, which means that the total resistance of that is going to be less. All right, so we're going to turn on the DC motor, make it turn, and then we're going to load the generator to make that thing work harder. Okay, so over here we're going to supply three-phase power: phase 1, phase 2, phase 3. Okay, and then we're going to get the excitation field also. So the power that we're going to get, the three-phase and the excitation, so that's going to be our total power supplied, which is going to turn it into mechanical power. How much of mechanical power can we do? We're going to know the speed. The speed is, in our case, 1800 RPM, rotations per minute. Okay, and so we're going to read the torque, and that's how we're going to get our mechanical power out of that one. All right. So that's our system that we're going to use. And don't worry if you don't know how to connect the resistors in parallel. I'll show you. But then when you take a picture of the load bank, then you're going to kind of compare that. And I encourage you to kind of look at this thing in that way. All right. Now, one concept that I want you to follow or to understand is the unity power factor, or the power factor. And I'm not sure if some of you guys already have downloaded the supplement notes. That's the next thing I'm going to open. I'm going to go over that. Oh, shit. All right. So let me cue this out. Here it is. Okay. One, that's the one, and here's our picture in picture. Okay, I'm going to try to zoom it in a little bit so we can see it. I hope you guys can see this thing clear enough. If not, you can follow the notes that you have downloaded, or you can just watch the video again, because I'm actually going to post this one here. All right. So this is well, that has to do with the lab report, section 7.2, and we're going to talk about the apparent power, the active power, also known as the real power, and we're going to deal with the reactive power. Okay, and then in that lab section 7.2, just have to remember that we are dealing with the per phase calculations. Okay, we're asked to do the calculations per phase. Let's give them some more light here. Okay, so things that we need to know about any kind of electrical circuit. Okay, in any electric circuit, the load doesn't take for the content, it just doesn't ask for the content, it just takes it. So basically, if you have a certain resistor applied to a certain voltage, it's not going to ask the power supply, can you give me 2 amps? It's going to try to take 2 amps. And if it can, it's going to try as much as possible to be close to 2 amps. All right, so that's, keep that thing in the back burner of your mind here, okay? Now, also what we need to know, the power that is used to do the work is called a real power. we're pushing a shopping cart. We're going to push that shopping cart at a certain speed. That shopping cart has certain mass, and we're going to push that up the hill or down the hill with a certain speed. That power that is being done by us, it is the real power, right? The speed over the distance and the mass. Right? Now, when we have to push this same cart up the hill, we're going to have to provide a little bit more power from our muscles in order to push the same cart at the same speed if it's up the hill. Right? So the true power stays the same because we're pushing the same cart of the same mass and at the same speed. Okay, but we have to provide a little bit more power because now we're going up the hill. So the power that is applied, the whole total power that is applied for us to, by us, push that shopping cart up the hill, it's going to be more than the power, than the work. So we're going to do more work than the work actually is going to be done because we have to push it up the hill with the same speed. So we're applying more work in order to we're applying more power in order to accomplish the same type of work, right? So this more power that we have to apply, that's called the apparent power. That's the total power supplied. Right? And then still, the work still being done by pushing the shopping cart from here to here, still the same work that's being done. So that's the real work. Right? So if we're pushing up the hill, we have to apply more power in order to do the same job. If it's on the flat surface, pretty much the power that we apply is going to be equal to the work that's being done. Ideally, of course, we're not going to get into the details of not philosophical, but the details of friction and stuff like. Just forget that exists. Okay. Now, when we're pushing this thing down the hill at the same speed, we're going to have to pull back a little bit, right? So still, the apparent power is going to be more, that we're going to apply more power than the work is being done, but we're just going to have different magnitude as far as vectors are concerned. All right. So it's going to cost us more muscle power to push it up the hill or having it done down the hill. Okay, if you can use that analogy. Okay? So so that's as far as the difference between real power. And now then there's the third type of power is going to be called the reactive power. We're pushing the shopping cart, okay, at the surface, flat surface. There's nothing pushing back or pulling down. So the reactive power, nothing reacts to it. Okay, we're just pushing. We can apply the same amount of power that the work is being done. Right. So that would be something that's called, keep that in the back, unity power factor. Okay, we're going to talk about more in a couple of minutes. Now, when we're pushing it up the hill, there is a reactive power that happens, and the reactive power is that the cart is pushing back on us. All right, so that's the reactive power. Now, when we do it down the hill, the cart is going to pull down a little bit, so we're going to have to compensate for the reactive power. So here's the reactive power that exists. Here's the reactive power that exists, and over here, the reactive power doesn't exist. So the unity power factor can be accomplished when the true work is equal to the total work applied, okay, which and the names of those powers are the work applied, the total power that is applied is called the apparent power. Right? The power that needs to be done, that accomplishes actually the work that needs to be done, it's called the true power or the real power. Right? And if we have something opposing this way, pushing that way, or pulling that way, then it's called the reactive power. Okay, so let's just keep going with this here. Wrong mouse. Okay. So here's what we're going to do. We're going to find the sweet spot on the synchronous motor. Remember when we had when we connected the amp meters? I'm just going to try to draw the machine that we have. Okay, so here's a voltmeter. Okay, here's 1, 2, and 3 amp meters, and there's another amp meter here that that measures the excitation field. So here's I phase 1, I phase 2, I phase 3. Okay. Now these are the amp meters that are going to measure the current that is flowing through the coils. So here's phase 1, phase 2, phase 3. Okay. And these are those amp meters that we're going to put here, here, and here. These are those 3 amp meters. And of course, we're going to connect that voltmeter here and here just to see what the voltage is across the phase. And that is going to measure the, remember when we're adjusting the field excitation current with that rheostat that we have? That is applying the power to the excitation field, basically to the rotor. So what we're going to do, and there's a switch. That is going to be the one of the most important things. Remember the switch here? Here's the DC power. That's when we just apply the DC power from our power supply. Plus minus, let's say. So that's going to be plus minus. And that is going to go through the field, through the amp meter, through the rheostat, and back to the other terminal here. So when we flip the switch on, the power is being applied. Okay? It is very important that, actually, you know what? I'm going to come back to that. We're talking about finding the sweet spot. All right, so when this motor is turning, and there is certain load here, okay, and in our case, we're going to have a resistive load in terms of a bunch of resistors being turned, connected in parallel, okay? That's our load. As we increase or decrease the load, we're going to make the current flow harder or easier through those stator windings. Of course, because if we want to remember, the synchronous motor turns at the same speed all the time. The speed doesn't change. The speed is determined by the frequency of the waveform applied. And since there's a revolving magnetic field, it is going to revolve according to the frequency that we apply from our power supply, the AC. And since it doesn't have any mechanical elements, it's going to start spinning right away. So at some point, we're going to adjust the rheostat here in order to provide more or less of the excitation current to the field. When we apply more current, we're magnetizing it more. We're applying less current, we're magnetizing it less. Now, that rotor is going to try its darnest to spin at the same time, at the same speed as the rotating magnetic field. That's the idea of the synchronous motor. That's just how it works. Now, when we load it more, we're going to make this work harder, because it's going to need more power to turn that thing, that thing. I just keep referring this to that thing, the rotor, right? Because the rotor is going to try to follow that at the same speed, but the load is going to increase or decrease. So of course, we're going to see the currents, and they're going to be the same over the phases. Now, when this thing is well balanced, okay, when we apply more current to the excitation field, we're not going to notice increase of or decrease of the speed here, okay? But we're going to notice the increase or decrease of these currents. The idea is that once we make this thing turn, this motor turn, we're going to adjust the current that goes through the excitation field in order to obtain the minimum current that we can. All right. Going to obtain the minimum current. Now, when the switch is turned off, there's going to be a lot of current flowing through that because we don't have that magnetized, this field magnetized, but what we have is something that's called a squirrel cage, and it's inside this motor, the rotor. It's just so it can self-start. Right? And then once it self-starts, it spins on the it spins with the same motion, same speed as the revolving field. Then we can turn the switch on and magnetize the field. Right? If we apply the power to the stator with this already magnetized when the switch is on, we're going to have an extremely strong magnet. And the rotating field is going to start spinning really fast. It's going to try to cut through the strong magnetic field that this thing is producing. So those two strong magnetic fields are really going to meet. It's not going to be able to turn right away. In fact, it won't be able to turn at all. That's why the synchronous motor is not self-starting on its own. We need help to start it. We need to bring this up to speed and then turn this turn the excitation field on so we can magnetize the rotor. So then it can just align just a little bit and start spinning on the with the rotating field, with the revolving field. Okay, if we have this thing on, this switch on, and we start that, we're going to try to move too much too quick, and something is going to give. All right, we're going to have a strong magnetic field being cut with another strong magnetic field, but this thing won't be able to turn as fast. So then it's just going to revolve around it. It's going to keep cutting. Those two strong fields are going to keep meeting at a very high rate, and we're going to create a mechanical overload or electrical overload. Okay? So we can actually burn the coils here. So so that's why I'm going to stress, and I'm stressing it now, make sure that this switch is off. Make sure that this switch is off before you start the motor. When the motor starts, you bring it up to speed. It's going to be quite quickly. It's going to take about 1 second or 2 seconds to bring it up to speed. Then you can apply the power, and as soon as you apply the power, the needles are going to move from here to about here, right? Just like that. So there's not as much power needed because we already have the rotor magnetized. Right? Then what we're going to do, so we're going to fine tune it. We're going to accomplish as much current as we need in order for that current to be the minimum that we can. We're not going to get it down to 0 because we're already turning that thing. So there's going to be current flowing through it. We're going to get it to the least amount that we can find. So if you increase the excitation field at some point, you're going to create more current flow through the windings. So what we're going to do, we're going to decrease the current, we're going to see the needle going down, 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 down. But if we decrease it too much, we're going to start seeing that needle going up again. So that's what I mean. We're going to try to find a sweet spot here, not too much, not too little. So we're going to find the least amount of current going through these phases here. So that's what I mean by the sweet spot. If this is just like pushing the cart up the hill or down the hill, we're going to try to make it, this thing is going to try to spin, this whole machine is going to try to spin at the same speed, okay? And if you give too much current, we're going to have too much current here because it's just going to compensate for the differences in power distribution, right? Pushing up and down the hill. If you go too little, it's also going to give more current in order to compensate for the differences, right? So that's why I'm saying they're finding the sweet spot. And that's actually, when we find the sweet spot, that's accomplishing the unity power factor, which we're going to talk about in a few seconds here. Okay. So during the lab, and I have this written in the past tense, but if you just compensate for the time line here, so we are going to adjust the field excitation to make the phase current minimal, so which is basically what I've just explained to you. Okay, this gives us the unity power factor. What that means, it means that the apparent power, and the apparent power is the total power supplied, right, or the power applied, is equal to the real power. So whatever we put in, we put that thing to work. We don't have to compensate because something is trying to spin faster. We're going to have to pull it back, or somebody is trying to spin too slow. We're going to give extra push in order to accomplish the same speed. All right. So here is what the power factor is. Okay. If you take the real power and you divide that into the apparent power, which is the total power, this is the power that is being used to do the true work. That's what we need. This is the power that we have to supply. And if they are equal to each other, then we're going to have something like number one. Okay? And if this thing is in watts, and if the other thing is also in watts, then what unit are we going to get? We are going to get no unit. We're going to get a unitless number. Right? So here's the thing. The power factor equals 1 if we accomplish the unity power factor, which means if those two are equal. Well, that's a very simple math here. All right, we're going to keep going with this. The unity power factor, or what I call it the sweet spot, revealed two things. Because once we accomplish that, and we measure the current and the voltage on the phases, because when we have that, we accomplish that unity power factor by finding the least amount of current that this thing needs to operate the way it is. It doesn't have to strain one way or the other. Then what we have to do is just, we can just find what the power is by using the power, by using the voltage and the current on each phase. We can add it to 3 and multiply by 3 because we're measuring the RMS values. So we are going to multiply those by 3. We're going to get the total power applied into this system here, plus the power that we need to excite the field. So that's going to be the total power applied. That's not going to change, all right? That it's going to have to be there. We can't make it disappear. It's going to change a little bit depending on the load, but it exists, all right? So the total power applied, but we just forget that for now. The power applied to this system here is going to be used to the power that we're going to be putting it to work. Now, in the reality of things, it's always going to be a little bit more power because we still have to apply, excite the field. But when we accomplish the unity power factor, it's going to mean that this whole machine is going to be operating in the most efficient way, right? So basically, the most efficient way means that we're getting as much power out of it as we possibly can, right? Right. Unity power factor. Okay, so the field current reference point from which we, what did I write here? The field current reference point for which we could go up or down to overexcited or underexcited. Field current from which we can go overexcite, underexcite. Okay, so the field current that we use to overexcite or underexcite the field, we're going to be varying. If you look at the lab here, which section is that? So this is this section of this lab here under the unity power factor. And how do we accomplish that? By making the phase currents draw the least amount that we can get. Okay. So basically, we are not overworking or underworking the machine. If we underwork the machine, we still have to apply the more power, right? So either way, we're going to lose power if we do not have the unity power factor. Okay, so we're going to measure the field current here. We're going to measure the phase voltage. We're going to measure the phase current, and we're going to get the torque out of it. And based on that, we can do a bunch of calculations here. So then we're going to lower from that unity power factor. We're going to lower that little bit. By that I mean the excitation current to excite the field. So we just will go over. Okay, so here's under excite. So we're going to lower it. We're going to apply a little bit less, and we're going to record the voltage and the current that and the torque. Okay. Now, the torque is not going to change. Anybody knows why? If we're turning something of a certain load, because the load here does not change, it stays the same. It's a bunch of resistors, and if we don't touch any of those switches here, we're going to keep the load constant. Yeah. And we're going to have the same speed. The speed is not going to change because that revolving field, that's not going to change unless we change the frequency of the applied power. So we have the same load, we have the same speed. Is the torque going to change at all if we manipulate things here? Anybody? If you're still awake, guys? Somebody answer. If we manipulate any of that, somebody said no. Good, yeah. Yeah. Thank you, David. All right. But, well, so that is going to tell us that that's going to reveal the true power that's applied. And the true power is the power that needs to be done to do the work. And under the true power, there's going to be a certain amount of current. So here's the unity power factor and certain voltage, right? And there's going to be torque here applied. Torque that we're going to be reading from the torque meter. Okay? When we underexcite or overexcite, is the torque going to change? Somebody answer something again. Anyone? Okay, we get the I think so from David again. Thank you, David, for being awake. All right. What was the question? All right. So if we overexcite or underexcite the field, is the torque going to change? That's the part that we're doing here. Remember, the load here doesn't change, and the speed doesn't change. That is going to remain constant. Again, Rodrigo says the torque will change. What's the formula for the mechanical power? Anybody? Remember we were calculating that mechanical power based on the speed? There you go. Tn over, so there's going to be the speed times torque over 955. So the speed is not going to change. The power that the load is not going to, power that is applied here is not going to change because the load doesn't change. So the torque is not going to change. So that is going to remain the same. So once you get the torque here, and if you don't change the load, the torque is going to remain the same. That's the real power. That's our key to finding out, knowing what the torque is, like we're about the synchronous generator. Is it going to throw us off the rails here? Can we ask it at the end? Just write it down. Cool. All right. We got a little bit of a thing going on here now. All right. Okay, so what we're going to do is we're going to overexcite or underexcite that. We're going to see this current change because, remember, the needle here, that phase is going to, because we're trying to adjust the rheostat in order to accomplish the minimum amount of current. Right? So of course, when we touch that, this thing's going to change. And which way is it going to go? It's going to go up. We go less, again, it's going to go up. So we're going to have more current no matter what. Right? And then based on that, we're going to be able to calculate the other powers that exist within the system. So let's just go back to this. Where are we here? Here. Okay. So the field current reference point from which we could go up or down to over or under excite the field, we're going to vary by 0.3 amps up and down from that reference point. Okay, so the field excitation, that's the rheostat we're going to operate. Okay, now what we just went through, the real power per phase in this case, when the unity power factor is accomplished, the real power per phase in this case is equal to the apparent power per phase. So now we know that the real power will not change. You gotta read it a few times because the speed doesn't change and the load doesn't change. So that's why. Now, so the real power in that case, we can calculate the real power per phase is going to be equal to the current that's going through the phase there and multiplied by the voltage. And since we're dealing with RMS, no problem. We get the power in watts. Right? So this is per phase. If you want to get the whole power that's in the whole system, then you just multiply it by 3 in our case. All right. And just remember that the real power is in watts. Okay, so here is, if you look at the right side of this, yeah, you look at the vectors, when the unity power factor is accomplished, the power factor angle is 0. Okay, basically the apparent power is equal to the real power. So the vectors just cover each other, and I kind of shifted them so you can see the red and the green, they cover each other. So the apparent power, and I put it in kilo VAs or kilowatts, but you can put it VAs and watts, all right? So that's the unity power factor. The apparent power is equal to the real power that's being done, being used to do the work. Right? I'll come back to that in a second here. Calculating the real power, notice when I adjust the field current, so calculating the reactive power. Okay. Now notice when we adjust the field current to either over-excite or under-excite the field, the values of the voltage across the phase and the current that goes through the phase, they will change. This means that the apparent power will be changed. Okay. So in that case, the apparent power is no longer equal to the real power. And now we have the power triangle right here. Right here. So the real power, we have established what it is, and that will never change. So we can assume that this thing is going to be constant. All right. Then the apparent power is going to be bigger because we're going to have something that's called a reactive power. Now the apparent power, we multiply the voltage and we multiply the current. But now the apparent power, that total power that's being supplied, because now it has an angle, we can't just have it in watts. We have to call it the VAs and just ignore that K here because that's thousands. All right. So that's volt amps. Because we're multiplying volts and amps. And if we look at now we have the right angle. So whatever is going to be plotted here, that is going to be the reactive power. The power that is going to oppose our motion, is going to oppose us from trying to make this thing spin faster or slower. And we're going to have to compensate for that in order to have the same real power accomplished. So the real power is in watts. Yeah. The apparent power is VAs, volts, amps, because we still multiply volts and the amps to get the power. And the reactive power, we also multiply volts and the amps, but in order to make some sort of a distinguish, we put a little bit of R on the end of it. So it's volts, amps, reactive. We call it VARs, VAR. Okay. You have this thing available for your download. So I encourage you to download that and try to print it in color, because if you notice, what I did is I put the apparent power in red, the real power in green, and the reactive power in blue here, just so you could see things in a pretty way, or you can make a reference much quicker to things. All right. So how are we going to calculate the reactive power? Well, we have a right triangle here with a right angle. Right. Since we got the right angle, well, we can use the Pythagorean theorem, right? So, or you can use the trigonometry as well as the sine and cosine things, or tangent, SOHCAHTOA. But whichever way you prefer for now, but we're just going to use the Pythagorean theorem, right? So the apparent power, which is the hypotenuse, yeah, if you take that length, that magnitude, I'm going to wait for that. Okay. All right, there we go. So the apparent power, this magnitude squared is equal to this squared plus that squared. Okay, and what we have here, the apparent power is no longer equal to the real power. So now we have this triangle. So that's what I said here. Now, remember, the real power will remain unchanged because the speed did not change and the loads did not change. So the real power that we're accomplishing here. So remember, here's the formula, all right? Now, based on the data recorded in section 4.2 of the Synchronous Motor lab, for each entry, we can calculate the apparent power, which is going to be at that moment, is going to be the voltage across the phase and the current flowing through that phase. So that's the apparent power. All right. So that we will have already. That's not going to change because the speed is not going to change and the load is not going to change. This one here we're going to get from the new instantaneous power. Now it's going to be continuous power. When we when we overexcite the field and remove our hand, the field is going to remain overexcited. Yeah, total. Yeah. So the phases are going to work harder to compensate for the differences in powers. So that's here, this apparent power, we can calculate from all the data that we're going to record in this table here. Reduce the load. So now we're going to reduce the load. First, we're going to bring it up to the full load. Right? And then we're going to reduce the load in 4 steps. In each step, record the current and the phase across the current and voltage across the phase. All right? It's not even Friday yet. All right. So current across the phase, voltage across the phase, and the torque. What do you think is going to happen to this torque here? Once we change the load, the torque is going to change, of course. Right? Where are we here? So we can calculate the apparent power by multiplying phase voltage and the phase current, and we're doing it per phase. Okay, remember, per phase. You gotta make sure that you pay attention to whether somebody's asking you in this lab to measure the whole to give you the whole total power, or just per phase. Okay, the real power you're going to have from the sweet spot here, unity power factor. All right. Now, we kept adjusting the when we were doing the synchronous generator lab, I asked you to keep the speed constant, because once you load the generator, the DC motor is going to work harder, and once you make the DC motor work harder, it's going to turn slower. So I kept asking you to adjust the speed of the DC motor to accomplish 1800 RPMs, right? All the time. Now, with all those with all these steps in our lab, we're going to keep adjusting the excitation field in order to accomplish the unity power factor at all times, right? So that's what we're going to have to pay attention to. Every time you change something, it might change. So just keep adjusting that. Okay. So here is the formula here. The apparent power squared equals the real power squared plus the reactive power squared. And that's from this triangle here, and that's the Pythagorean theorem. Okay. Now, if you want to calculate the reactive power, so the reactive power squared equals apparent power squared minus power squared, because we derived that formula from this, right? Whatever you do to one side of the equal sign, you have to do the same thing to the other side, okay? Now, but this is going to give us the reactive power squared. So we root it, we square root it. So if we square root one part, we got to square root the other part. So that's how you can calculate the reactive power in each case that we're going to do. Okay. And that's pretty much it for today when it comes to our lesson. Now, whoops, that's not what I wanted. That's what I wanted. So the C18, you have those now. Read through those. I'm going to encourage you to read through those and try to look at some of the examples here that we're doing. Now that, let's say, for example, this class 22, the C22, that's talking about the same thing, about power factor here. It's just a little bit different spin on that, right? But if you get these notes that I gave you, and you get these notes here that you're seeing, that you're downloading, you'll be able to download both of them. I'm pretty sure you will have no problem understanding this, okay? Now, I'm going to ask you to read through some of that. So class 19, class 20, let's see what, this is the synchronous motor. All right, we can just go quickly over some of the concepts here. What I'm going to do is I'm going to get rid of my picture here. So the synchronous motor here, as we said, it's just a review of what we said. It converts electrical power into mechanical power. Let me just zoom a little bit here. Synchronous, what does it mean that is synchronous? That means that the rotor, remember we went over at the beginning of this lesson here, that the rotor is going to synchronize the magnet that is being created by the electricity, the DC electricities. We're going to have a magnet, electromagnet, or if you have a permanent magnet, that's fine too, right? Then, but you won't be able to self-start it. So that's why we use electromagnets, so we can control the strength of the magnetic field produced by the metal bar, if you will. Okay? It is going to follow the is going to follow the rotating magnetic field produced by the stator winding. So that's why it's called synchronous, that the speed of the rotor is going to synchronize with the speed of the revolving magnetic field produced by the stator. Synchronous machine. Input, we got three-phase electricity. Output, we get mechanical power. Uses, application, heavy industry. That's all it says here. There's other input power that we have, but we're going to talk about, so you have seen this already in the last class. Now, so we analyze that. So it's the same principle here on the right hand. Okay. Here's the field coming down. Here's the EMF generated. And here's the motion. Whether you apply the motion, it's going to create the EMF, or we're going to apply the magnetic field and run current through it, it's going to apply the motion, it's going to create motion. Now, here is the stator winding. Here's the stator winding. So A to A. That's the one winding here. Oh, I can't do that. And then there's another winding, and there's another one. So there are three windings here, and they're 120, sorry, 180. I keep getting the 180 stuck in my head. 120 degrees apart. What we're going to get is when we apply the three-phase to each winding, 120 degrees apart, the waveforms, that's what's going to create the revolving magnetic field around the stator, and that thing is just going to follow it. So what does it say here? Three-phase winding, stator, we have three-phase winding, supply three-phase AC voltage. Rotor, we're going to create a magnetic field by supplying the DC excitation current. So the stator is going to have three-phase voltage, three-phase current, and rotating magnetic field. That's going to produce the magnetic field. Rotor magnetic field by the Lorentz force. The Lorentz force it's going to rotate because it's going to try to follow that. We are going to skip some of that here. Stator, carry on three-phase windings. So we just So this example, we're going to tackle that next time we see each other. This is the number of poles here we're talking about. Synchronous motor, power connects. Okay, so we already done that. Lorentz force, apply the right, well, the left-hand rule in that case. Then three-phase windings, stator, three-phase windings, rotor magnetic field. And the speed is going to equal to 120 times frequency times number of the poles. And we're going to get some of the, exercise that have to do with that. C21, what do we get here? Synchronous motor. Is that the number of poles here? Here's the power triangle that we talked about. So just read through that. You're going to get a different spin on this, but it's going to be the same thing that we just talked about. We just did get 21. Yeah, we just did that. C22 is that okay, so here's the power flow. Okay, we talked about the power factor here. The power flow that we have, let me zoom it a little bit. What is it that we are applying to that? We're applying the AC power here, and we are applying the field excitation power, and get out. And we're getting the mechanical power out of that. So this AC power plus the excitation power is going to be always more. And then accomplishing the unity power factor is going to make it, it's not going to, this is never going to be equal to that. We're always going to have some losses. Just because, like, for example, just think about it. Even if you have this motor not running, and we turn on the excitation field, we are already losing power when this thing is not even turning. Right? So that has to be calculated into adding the power as far as power consumption, total power consumption. So we are adding the power that we supply to make it turn. We're adding the power supplied to create electromagnet out of the rotor. And we're going to always get less power than that. And whatever the difference is, that's going to be the losses. Of course, there's going to be some other losses, friction, the air, some of the power is going to go into heat. So yeah, it's going to be always, there's other things that need to be considered, okay? So, but if you apply, if you divide the output power over the input, the total applied power, you're going to get the efficiency, and you're going to get the losses. Okay? Now, when we talked, one other thing is that we talked about that the synchronous motor is not self-starting. It doesn't self-start. And we talked about why. If we completely magnetize, let's see here. Here are the windings, 120 degrees apart. And over here you have this rotor that's magnetized. Let's say the switch is fully, it's on, we got the excitation field, this thing is fully magnetized. We're going to have extremely strong, quite strong, revolving magnetic field that is going to turn. And we're going to have a strong electromagnet here. It's going to try to make it turn, but before this thing has a chance to move, the magnetic field is going to move, right? It's going to start, keep spinning. So we're just going to keep hitting that and hitting that and hitting that. So that's not good. It's not going to turn, but the force is going to act upon each other, and they're going to be really, really interacting in a way that we don't want, right? So then something is going to let go, something's going to give. But we need, so the one thing is to bring it up to speed, and you can just do a crank, mechanical crank, and start this thing spinning with the same speed. And once the same speed is accomplished, but how do you know you get the same speed? And then you can magnetize it so that rotor is slightly going to just kind of shift a little bit, but it's going to, so it can align with the magnetic field, but it's going to start turning, and the power is going to be applied, and the speed is going to be maintained. Right? So what do we do in order to self-start the motor? Well, the rotor has the field windings, but also what it has the something that's called a squirrel cage inside. Actually, it's kind of embedding the whole. So the squirrel cage is just like the hamster kind of running, but instead of that squirrel, I guess 100 years ago they had squirrels, not hamsters, as pets. Who knows? But it's called a squirrel cage. right? And here's the axle that it turns, right? So what's going to happen is that once the magnetic revolving magnetic field revolves around that, and remember the Lorentz forces here, it's going to create EMF in those are metal rods here. There's a metal rod, and there's another metal rod, and there's another metal rod, and there's another metal, so just full of metal rods from one ring to another. Right? It's going to create an EMF force, which is going to produce the motion. So it's going to start spinning out, but it's not strong enough to break anything. It's just strong enough to make it start spinning. And before long, that squirrel cage is going to spin with the same time, the same speed as the rotating magnetic field. So that's how we're accomplishing the speed. And then once we accomplish that, then we flip the switch, we magnetize it. So now the whole thing is at a full speed. We're just going to align it and make it more efficient. So that is the idea of something that's called the induction motor that we're also going to talk about maybe a couple of weeks from now. Okay? So that's how we self-start the induction motor. Okay? That's pretty much it for today, as much as I want you to know the concepts. What is it? We're going to see each other probably Thursday or something like that. We're going to tackle some of the calculations. And based on that, I'm going to give you, later on, I'm going to give you a test, and how and when I'm going to still announce, okay? It's going to be online test. When I do my tests are online, and I'm going to design my own questions for this. And it's going to be the difficulty is going to be accordingly difficult, so you can actually get your creative juices flowing or your knowledge juices flowing, so you could answer some of the questions. It's going to be a little bit more detailed. So they're not going to be the questions from last year. They're not going to be questions from the previous year. So if you talk to anybody from the previous years, forget those questions. All right. Okay. Now, Dave, was it Dave that had the question about the synchronous generator? Was it about the lab, or was it up on the synchronous generator? Okay, what will happen if a synchronous generator, if we let 3 phases of the stator windings unbalanced for at least 30 minutes or more? I mean, we put different loads on each phase. Oh, that depends. That depends how much load like that can be. All the systems are slightly unbalanced anyways. Ideally, we want to have things balanced. Okay, but really, you could probably see on the well, that depends on the rating, how much of the road current is going to how much it can be unbalanced. Okay, so you're going to have you're going to have differences in currents. So one phase is going to try to feed another, and if it's too much, then you can overheat the motor. Okay? And if you overheat the motor, the windings, the winding, how much unbalanced, I can't tell you. All right. In fact, I just showed you that during the lab, I disconnected one of the phases and the motor was running. Right? So the motor was running. The 1K of what? 1000 ohm, 1000 watts. I can tell you. It depends how much what this thing is made of. In some of the specifications in the generators or the motors, you're going to see some of the specs saying that you can throw it off balance this much, or the voltage per phase is going to it's within the region. It's there's no way, you know, you get your ankles, you hurt your ankle, how long you're going to walk before you have to go to the doctor, right? So I can't I can tell you exactly how much, right, and for how long, right, because depends on many different things. Okay, but what I'm going to do is, that's why there's a reason why I have asked you to connect all 3 phase meters, because what we used to do before, it was just enough to connect one of the phase meters, the phase currents, because the other ones should be the same, so we have a balanced system. But in the generator, with some of the stations in the generator, I disconnected that one of the phases. This thing is still running, but the other ones took over, right? The currents have changed, right? And I didn't want to leave it for too long. Okay, I connected right back. Also, I'm going to show you some other things, that what's going to happen if all those 3 phases are not connected. What kind of symptom I'm going to see. And by hearing that sound or feeling that vibration, you'll be sort of be able to guess what's wrong with whatever the machine you're going to deal with. Okay. Later on, when this thing is running, can we disconnect one of the phases? Well, why don't we try? Right? Not going to be able to do it for long, because I don't want to damage the machine. But I'll be able to disconnect that for a little bit. And actually, when you have a lab with me, Dave, was it Dave that's asking me the question here? No, it was Rodrigo. Yeah. So just ask me to disconnect one of the phases and see what happens. Yeah, thank you, Rodrigo. Okay. So that's it for today, guys. And I will now. Did somebody else join here? Did everybody have a chance to do the previous lab? Are we all up to date with the labs? Because this lab is what? This synchronous motor that we're going to do for the next 2 weeks is going to be lab 6, which is synchronous motor. Is there anyone that still hasn't done lab 5? If there is anyone there, and if you watch the video and you can talk to them, I'm gonna keep asking people. If you haven't done lab 5, please let me know so we can find a time for you to so you could do that. Okay. All right. So that's it. So my quick test questions are based on FOL material. Based on FOL material, basically everything that we experienced together during the lectures, the FOL, and we're going to, I'm not going to leave you hanging. If I didn't tell you something, if I didn't teach you something, I'm not going to evaluate you on it, all right? I'm going to try my darnest to accomplish everything that we have with the, and cover all the bases that need to be covered. And it's going to be also based on the knowledge that we get from the labs. But don't worry, I'm not going to be too ridiculous on you. So if you pay attention and if you're awake during our sessions, then you should be fine. Okay, guys, that's it for today, and I'll see you when I see you.